Section 14.5 introduces binomial experiment. So 4 criteria need to be met in order for something to be a binomial experiment. The 4 criteria are right here. The first one is that there is a fixed number of trials. The second one is that each trial is independent of the others. Number 3 would be that there are exactly 2 outcomes for each trial. And finally, the probability of success must be constant. So let's look at 4 different experiments and decide if they are binomial experiments. So number 1, there's a telephone survey that's going out to 200 people to ask if they voted for George Bush. Number 2, it's counting the average of number of dogs seen in a veterinarian's office daily. 3 is you take a survey of 50 traffic lights in a certain city at 3 p.m., recording whether the light was red, green, or yellow at the time. And the 4th experiment is you are at a fair playing Pop the Balloon with 6 darts. There are 20 balloons. 10 of the balloons have a ticket inside that says win, and 10 have a ticket inside that says lose. Okay, so the first experiment. Let's see if it meets the first criterion. We have a telephone survey that asks a group of 200 people. Does that fit the first criteria, which says it's a fixed number of trials? And the answer is yes, there's only 200 people that are surveyed. Number 2, we're counting the average number of dogs seen at the veterinarian's office. And this does not meet the fixed number of trials. Okay, there could be 10 dogs in the office one day. There could be 100. There's not a fixed number of trials happening. All right, number 3, you take a survey of 50 traffic lights. We can stop there. 50 traffic lights is our fixed number of trials. And finally, number 4, you are at a fair playing Pop the Balloon with 6 darts. Yep, fixed number of trials. 6 of those darts we throw. Okay. Next, each trial is independent of the other. Let's see if that happens here. For number 1, when you survey 200 people and ask them if they voted for Bush, is it an independent experiment, meaning like the first person you ask, if they said, yes, I voted for Bush, does that affect whether the second person voted for Bush? And the answer is no, it doesn't. So it's independent. So that meets the second criteria. Number 3, you take a survey of 50 traffic lights in a certain city at 3 p.m., recording whether the light was red, green, or yellow at the time. This trial is independent because if you look at the first light and it's red, that does not affect whether the second light will be red, yellow, or green. So number 3 meets. Number 4, you are at a fair playing Pop the Balloon with 6 darts. There are 20 balloons. 10 of the balloons have a ticket that says win. 10 of the balloons have a ticket that says lose. This is not independent because if you throw a dart and you pop a balloon with your first dart, the second dart on whether it's going to hit a balloon that says win or lose is now affected because let's say the first dart you throw hits the balloon and inside it says win. Now when you throw the second dart, it's no longer 1 out of 2 chance to get a win or a lose. The win, we have to take away one of the wins, so now there's only 9 wins out of 19 balloons left. So this would not be a binomial experiment. The third bullet point says that there are exactly 2 outcomes for each trial. So for the experiment number 1, when we're asking if they voted for George Bush, there are only 2 outcomes. The answer is either yes, you did, or no, you did not. So that meets. Number 3, we are looking at the traffic lights, and they're going to either be red, green, or yellow. There's not 2 outcomes, there's 3 outcomes. So this is not a binomial experiment. Let's look at number 1 and see if it meets the final criteria. It says that the probability of success is constant, and it does meet it because it's always going to have a probability of 1/2. Okay, so on your own, I want you to pause the video and I want you to answer example 1, part A and B, and let me know if they are binomial experiments, and I also want you to explain why they are or why they aren't. For part A in example 1, the answer is yes, it's a binomial experiment because if you're going to roll a cube labeled 1 through 6 and you're going to roll it 10 times to see how many 3s are rolled, it does have a fixed number of trials. That's 10 of them. It's independent. Whatever you roll on the first time does not affect what you roll on the second time. It only has 2 outcomes. Either you roll a number 3 or you don't roll a number 3. And the probability of success is constant because it's always going to be 1/6 each time. 3 is only on the die once. Therefore, 1 out of the 6 numbers would make it a yes that you rolled a 3. For part B, the number cube labeled 1 through 6 is rolled until a 3 appears. This is not a binomial experiment because there's no fixed number of trials. All right, example 2 is a little bit different. We have a number cube labeled 1 through 6. It's rolled 4 times. And we want to know, what is the probability of rolling a 5 exactly 3 of those times? Okay, so the solution to this is that we are going to first, let's make R represent rolling a 5 and N represent not rolling a 5. So we have, this is a binomial experiment because it meets all 4 criteria. We have our 2 outcomes, and we're going to expand R plus N to the 4th power. That will give us the probability of rolling a 5 exactly 4 times, rolling a 5 exactly 3 times, rolling a 5 exactly 2 of the times, rolling a 5 1 of the times, and rolling it 0 times. So really, when we expand the binomial, I'm not going to spend the time to do it, but what you're doing is you're doing R plus N times R plus N times R plus N times R plus N. Okay, mathematically you can do this. It'll take some time. I'm going to give you the answer. So it'll be R to the 4th power plus 4R cubed N plus 6R squared N squared plus 4RN cubed plus N to the 4th power. And what each of these terms means is the following. So this means that you're going to roll, because R represents rolling a 5, so you're going to roll a 5 all 4 times. This right here, the second term, represents rolling a 5 3 times and not rolling a 5 1 time. Don't worry about the number 4 in front. Just worry about this portion of it. So R cubed N, 3 times rolling a 5, 1 time not rolling a 5. Okay, and you could probably guess that this term right here means rolling a 5 twice, not rolling it twice. Over here we have rolling it once, not rolling it 3 times, and the last option is not rolling a 5 all 4 times. Okay. We wanted to figure out what is the probability of rolling a 5 exactly 3 out of those 4 times. So that's represented by this term right here. So we're going to use that information. We're going to say the probability would be 4 times, and then the probability of rolling a 5 is 1 out of 6. And we're going to cube that, times N, which is the probability of not rolling a 5, and that would be 5 out of 6. So now when you multiply across, you end up getting 5 out of 324. In decimals, that goes to 0.015, which as a percentage means that you have a 1.5% chance of rolling a cube 4 times and 3 of those times getting a number 5. Okay. You are now going to move on to the activity, which will be what you're going to do for the rest of the day. In this activity, you will compare the experimental probabilities of tossing 2 coins to the theoretical probability found by using the expansion of the binomial h plus t squared. H is going to represent heads, t will represent tails. So in this experiment, you're going to need 2 coins. Let's expand this binomial. So h plus t squared, this one is a lot easier than example 2. When we FOIL, we end up with h squared plus, we have ht plus ht, so 2ht plus t squared. And what does this really mean? Well, h squared would represent getting heads, so 2 heads and 0 tails. Because remember, you're taking a coin, 2 coins, tossing them at the same time. And this would represent you have 2 heads. This right here, the middle term, would represent getting 1 head and 1 tail. We're ignoring the number 2 at this point. We're just saying what these represent. And the last term would be t squared. So t and t would mean you have 2 tails. That means you did not get any of the heads. Okay, let's rewrite that. Now, what each of these means is that if we have HH, the probability, and there's technically a 1 in front. So this would be 1 times the probability of getting heads on a coin is 1/2. Probability of getting heads again is 1/2. So this multiplies to give you 1/4. You have 1/4 the probability of tossing 2 coins and getting 2 heads. Over here, we have 2 times h times t. Okay, so 2 times probability of getting heads is 1/2. Probability of getting tails is 1/2. So 2 over 4 simplifies to 1/2. So you have 1/2 the probability of getting a heads and a tails. And let's write here h squared. This would be for ht, 1 of each. And then the last one, if we have 1 times t, because that's t squared, it'd be 1 times to get a tails, it's 1/2 chance. To get a tails, it's 1 out of 2. Multiply this, we get 1/4 the probability of getting 2 tails. Okay, that is the theoretical probability, and you're going to refer back to this when you're doing your experiment. So it's a pretty simple experiment. All you're going to do for number 1 is you're going to take 2 coins, you're going to toss them at the same time and record. If you end up getting 2 heads, you'll make a tally mark here. If you end up getting 1 head, 1 tail, you'll make a tally mark there. You are going to do this 20 times and record your data. Then calculate your probability from your experiment here in part B. And then, so it'll be out of 20, and then you'll have to simplify. So out of 20, out of 20, out of 20, and simplify. You're going to compare the probability in the binomial expansion to your experimental probability results. And what do you notice? So you'll compare these results to the theoretical probability. Okay. For number 2 in this experiment, you're going to do the same thing, only you're going to toss the coin 50 times. Feel free to keep your first 20 times the same and then toss it just another 30 times and add your data to number 2. Let's see what happens when comparing the experimental probability to the theoretical probability when there's 50 coin tosses. You'll probably be out of time after that, but if you're not, or if you just want to spend more time on math today, you can do this with 100 tosses and see what's happening when you're comparing your experimental probability to the theoretical probability. Once you're done, you'll upload this to Google Classroom.